In this lecture, we will study calculation of electric field in uniformly charged spherical shell using Gauss law. We have studied many applications of Gauss law. In the last lecture, we have studied the application of Gauss law in calculation of electric field in infinitely long parallel plates and their applications. This is also very important application when we have spherical shell uniformly charged, or then in that case we have to take spherical Gaussian surface to calculate the things. We will discuss these details here. We will able to learn how the Gaussian surface can be assumed, how the field can be calculated, and interestingly, if the some charge is there on the outer shell, then how we assume that the virtual charge should be the inside part of the shell. Such type of details can be assumed using this. Gauss law has many applications. We have discussed some application in the previous lecture and some we will discuss here. We know that the Gauss law can be used to solve complex electrostatic problems. The problem involving unique symmetries like cylindrical, spherical or planar symmetry. Also, there are some cases in which calculation of electric field is quite complex. If you are having large number of charges or the electric field calculation is complex, that involves tough integration, so it will require a lot of time. Gauss provides an alternative. Gauss can be used to simplify evaluation of electric field in a much simpler way. We can apply Gauss law in many ways. Like, first thing is, if we want to calculate electric field using Gauss law, choose a Gaussian surface such that the evaluation of electric field become easy. Make use of symmetry to make problems easier. Remember, it is not necessary that the Gaussian surface to conclude real surface. That many times the Gaussian surface do not coincide the real, and it can be inside or outside the Gaussian surface. We can take these steps to calculate electric fields. Now we are discussing some examples from the electric fields calculation. Another application is electric field due to uniformly charged particle shell. Now we have a shell which is uniformly charged, and the charge density we have assumed here as sigma. Since the charge is on this shell, the electric field will be on outward direction. Now we want to calculate electric field at various places: inside the shell, on the shell, outside the shell. Let us consider the first case in which we want to calculate the electric field outside the shell. Suppose we want to calculate electric field at a point, and that point is, let this point is P. The point P is here. I have shown, better to use red color. This is point P, and we want to calculate electric field at this point. Then we know the rule. First we have to calculate a Gaussian surface. We have used here a Gaussian surface of spherical shell, which include the original shell already. The radius of the original spherical shell is capital R, and for the Gaussian surface we have used small r. Now we are saying the point that P is outside the shell, then R is greater than capital R. If R is greater than capital R, then P be a point outside the shell, and R is the distance from the center for that point where we want to calculate electric field. Now at this surface that we have created, that's called Gaussian surface. It's a closed surface, symmetric surface. The flux crossing the Gaussian surface in outward direction can be written as E dot dA. E dot ds or EDS, since both are non-integrally and integrally. So we know that the total area, surface area of the sphere will be 4 pi r square. So this is E into 4 pi r square. Now by Gauss law, you can write E into 4 pi r square is equal to Q over epsilon 0. Or you can calculate, so E can be written as E upon 4 pi epsilon 0. So this is the field whenever you are outside the shell, where r is the distance from the center. Can you remembering something from here? Yes. If you want to calculate, if suppose the charge is on the center, now charge is not on the sphere but on the center. And if you want to calculate, this is your sphere and this is your Gaussian surface, then this is, suppose this is r, then the field will be same. Field will be same if your charge is on either on O center or on the shell. The electric field at a point outside the shell will be same as if the total charge on the shell is concentrated at its center. That is sure. So it gives a very interesting conclusion to us. Either you put your charge on the shell or on the center, the answer will be same. Another interesting case is, suppose the shell is there and you want to calculate electric field on the shell. The electric field E for P point on the surface can be done as E is equal to 1 upon 4 pi epsilon 0 Q over R square. It means here we have just used small r is equal to capital R. So you can calculate electric field. So in this case, when a point is inside the shell, we are considering a point P inside the shell at a distance r from the center of the shell. In this case, we can construct a Gaussian surface with radius r prime. The total flux crossing the Gaussian surface normally we have is an outward direction, and since there is no charge enclosed by the Gaussian surface, so according to Gauss law, if there is no charge, the field due to uniformly charged thin shell is zero at all points inside the shell. That is the reason when we calculate the flux will be zero. Actually, inside the shell, we have assumed there is no charge. Charge is always living outside the shell. We can draw here to explain. Suppose this is your shell and you have distributed charge here. You want to calculate if this is the center O and you want to calculate the field at this. We assume this, then field is all charge is always on the outside. It can't be inside. So like this. If it is there, then the charge inside will be zero. It looks sometimes surprising, but it is there. The charge is inside zero may have lot of applications. Suppose you are caught in thunder shower and too much lightning is there outside. Then suppose you are driving a car, then should you come outside the car to save you, or should be you inside the car to save you? It's a very celebrity question. Yes, you are safe inside the car. Why? Because if the thundering strikes your car, then if you are inside the car, then you will not feel any electric field there. It will only live outside the your car, because your car in that case behave as a shell, not a spherical exactly, but it is a shell. That is why the shell is a very important concept. You are having a charge outside this, but inside you will not experience anything. And this we have shown using Gauss law. Gauss law have many applications based on this. Even you can develop many applications on the basis of such type of behavior. So we have discussed in this lecture electric field due to spherical shell. In the previous lecture we have discussed electric field in the parallel sheets. We have also discussed many applications and few numericals in one lecture. This completes your Gauss law and its application part. Remember, Gauss law is one of the most important law of Maxwell equations. It deals with electrostatic charges, charge when are statics. If you want to calculate electric field in several conditions, the calculation is very difficult. But by the use of this Gauss law, the calculation is very easy. Easily you can calculate many things in the electrostatics, and this is the beauty of this law. This is the one of the celebrity law for electrostatics. In the case of electromagnetics, we will also discuss that law, Gauss law for magnetostatics, and that is always zero. Del dot B is always zero, which shows that magnetic monopoles doesn't exist. But as far as electrostatics are concerned, monopoles exist. Electric monopole exists. That is why you can calculate field due to one charge, two charge, three charge, and so on. We have discussed these things in detail here.